Welcome back. We'll continue our discussion of describing kinematics in one dimension. I should mention kinematics is just a fancy word for motion. So there's kinematics. In one dimension means we're moving basically in a straight line. So whether an example could be this car moving in a straight line across the desert, or it could be a ball thrown straight up and coming straight back down. Those would both be examples in kinematics in one dimension. Once we add a second dimension, the car going around a curve, or a football where we have both vertical motion as the football goes up and down and horizontal motion as the football moves in the direction of the throw, that will be two-dimensional motion, and we'll cover that in our next section. But for now, we're talking about kinematics in one dimension. We've talked about a few topics so far, and I just want to refresh that we've talked about velocity. Velocity is the description of how fast something is moving. So it's a measure of meters per second. How much distance do we travel in a certain amount of time? Having used the word distance, I should also clarify again that there's a difference for this course between distance and displacement. Distance is the length of the path actually taken, whereas displacement is the length between your starting position and your final position, regardless of path. So we've talked about velocity. Instantaneous velocity just gives you a snapshot of velocity at one instant in time. And we're now up to talking about acceleration. So in this video, we'll talk about acceleration, constant acceleration, how to approach problem solving, and then an example of constant acceleration, which is falling objects. And we'll have a little bit of discussion of graphical analysis, but I've actually tried to move the graphical analysis discussion throughout each of the sections where it's relevant. So our next concept is acceleration, and acceleration is a rate of change of velocity. So let's think about what that means. So once again, we know what distance is. Let's say you're going to move between one hand and another. You toss an object. I've got a little object, and it's going to go a distance from one hand to the other. So it's traveled some distance, and if I just measure this from the starting point to the ending point, that would be the displacement. The speed at which it travels from one point to the other is the velocity. So if I take my distance and divide it by the amount of time it takes, I'll get the velocity. The acceleration is how the velocity changes. So if I can get things launched and have it move at an absolutely constant speed, I will have no acceleration once it's moving. Obviously, it starts from rest here if you're watching, but once it's moving, if it moves at an absolutely constant velocity, then the acceleration is zero. If it starts and it has some rocket on it that speeds it up as it goes, then it is accelerating. There's a rate of change of velocity. There's a positive acceleration. Or if it starts really fast and slows down, so it's going fast and then slows down, it would be decelerating or slowing down, but there'd still be it'd be a non-zero acceleration. And we'll talk about the difference between deceleration and negative acceleration during this video. All right, so acceleration is a change in velocity. So you want to make sure you have really clear in your head the terms distance and displacement, and then velocity, the rate at which we move, and then acceleration, how the rate at which we move changes. So they are different. Okay, acceleration has both a magnitude and direction, therefore is another example of a vector, as was velocity, as was displacement. And we will talk more about vectors again in the next set of videos. Quantitatively, we can calculate the average acceleration as a change in velocity divided by time. That's putting this statement into a more mathematical form. When we find a rate of something, we're dividing by time. So the rate of change of velocity is the change of velocity divided by the time elapsed for that change to occur. That gives us our average acceleration. Algebraically, we usually write acceleration. We designate acceleration with an A for acceleration. A bar over the A tells us average. So this A bar is for average acceleration. And just like with velocity, there are a myriad of ways we can represent this. But the basic idea on the right is it's a change in velocity. Again, the Greek symbol delta we use to represent change. So it's a change in velocity over change in time. And we could represent that as, say, final, it's always final velocity minus initial velocity over final time minus initial time. But for final velocity, initial velocity, we might designate that as v2 minus v1, or vf for v final minus vo for v original, or other examples just like we saw for velocity. These are two of the most common. This second one is used in OpenStax. This first one is sometimes used in Giancoli. All right, so let's look at an example. Here's a little sports car, and we're going to look at how this sports car moves through time. Here it is starting out, and we're starting to represent things algebraically. So our time initially, or time 1 is 0, and the initial velocity equals 0. So this car is at rest, and we are going to accelerate. We hit the gas, and we're going to accelerate at 15 kilometers per hour every second. So that means after 1 second, t equals 1 second, we've gone from 0 velocity, and after 1 second, we've accelerated by up to 15 kilometers per hour. As we change our speed, our velocity by 15 kilometers per hour, that's the velocity every second. That's the time elapsed. So with this constant acceleration, after 1 second, we're going 15 kilometers per hour. After 2 seconds, we've increased our velocity by another 15 kilometers per hour. We're up to 30 kilometers per hour. And after 5 seconds, we're up to 75 kilometers per hour. You could just keep adding 15 kilometers per hour until you've done so 5 times to get to that value. To check that this is all consistent, having a starting and ending value, we call this t1 and this t2, we can calculate the average acceleration as, again, a change in velocity over time elapsed. If we look at our algebraic equation for average acceleration, it's our change in velocity over change in time. Our final velocity here is 75 kilometers per hour. Our initial velocity was 0. So in the numerator here for calculating average acceleration, I have 75 minus 0 kilometers per hour. And then for the time, t2, our final time is 5 seconds. t1 was 0. This is t2 minus t1, or 5 minus 0. And that gives us 75 kilometers per hour divided by 5 seconds, or dividing 75 by 5, we're back to 15. So we have an average acceleration of 15 kilometers per hour per second, which is just what we said when we started. So the equation holds up, everything is consistent. All right, thinking back to section 1, I don't like to combine time units like this. In some ways, in this case, it makes sense. You might be more familiar with kilometers per hour or even miles per hour in terms of the speed of a car. And so it might make most sense to you to think things through as, we're changing our speed by 15 kilometers per hour every second. But the physics purist in me wants to clean up the unit, so I have done that here. So this is the solution we had so far, where we worked out 15 kilometers per hour every second. And up at the top is just repeating our equations. So let me redo this. I'm going to convert 75 kilometers per hour to meters per second. A nice opportunity for another example for a conversion factor. So I have 75 kilometers per hour. I want to get to meters per second because that's the SI unit. So I'm heading to SI units. And so to get rid of the kilometers, I know 1 kilometer is 1,000 meters, and I set up my conversion factor so kilometers cancel. And then for hours, I could do 1 hour is 60 minutes and 1 minute is 60 seconds, or I could just do 60 times 60 right up front, which is what I did here. That would equal 3,600. And I have a conversion factor that 1 hour has 3,600 seconds. And I've set that up again so that with hours in the denominator here, that canceled my hours in the numerator here. I'm left with units of seconds. And once I've canceled all my units, I just have left meters per second. The kilometers cancel and the hours cancel. So I have units of meters per second. That's good. So then I'll go ahead and do the math. 75 times 1,000 divided by 3,600. If you run that through calculator, you get 21. So 75 kilometers per hour is equal to 21 meters per second. Now I can go through the math again as another example. So average acceleration is final minus initial velocity over final minus initial time. So my final velocity here, instead of 75 kilometers per hour, I'll put in 21 meters per second. Initial is still 0. Time is still 5 minus 0. So 21 divided by 5 gives me 4.2, and the units now are meters per second squared, which represents acceleration in SI units. All right, one thing you'll notice, let me just go back to this example one more time. When we have a constant acceleration, as we see here, our velocity is changing, right? if the velocity weren't changing, our acceleration would be 0. So with a constant acceleration, as shown here, our velocity is consistently changing. All right, let's consider some other scenarios. And first I'll note that acceleration, as I mentioned before, is a vector. That means it has both magnitude, how rapidly we're changing our velocity, and it has a direction. And we'll talk more about direction as we go here. So the previous example showed positive acceleration, and let me just show you here. In the slides that I'm showing, velocity is shown with a green arrow, and you can see as we went forward in time, that green arrow got longer and longer, corresponding to a higher and higher velocity. The acceleration is shown in this yellowish orange arrow, and it is to the right. And I usually assume positive is to the right. So we had both positive velocity and positive acceleration in that case. And when acceleration and velocity are in the same direction, the velocity increases. All right, in this case, we have a velocity to the right, but our acceleration is back to the left. So this is an example of if you were hitting the brakes. So you're going along at 15 meters per second and you hit the brakes and you start to slow down. We have a negative acceleration here. Acceleration is to the left. And if we did a little bit of math, if we make this the initial condition, time 1 is 0, we start at 15 meters per second, we apply this negative acceleration of 2 meters per second squared, then after 5 seconds, our velocity will be down to 5 meters per second. So we will have slowed down. And if you're wondering how that works out from second to second, you could think it through. We start at 15 meters per second. After 1 second, we're going 13 meters per second. After 2 seconds, we're going 11 meters per second. After 3, we're going 9. After 4, we're going 7. And after 5, we're going 5 meters per second. So you could, by force, figure out how this changed. Let's again check our values. We can do our equation for average acceleration, final minus initial velocity, final time minus initial time. So our final velocity is 5 meters per second. Our initial velocity is 15. So 5 minus 15 is minus 10. Final time was 5 seconds. Initial was 0. 5 minus 0 is 5. 10 divided by 5 is 2, and there is a negative there, so we get minus 2 meters per second squared, which is indeed the value of the acceleration we said was acting in this problem. So there is a difference between negative acceleration and deceleration. So negative acceleration is going to be when the acceleration is in the negative direction. So if we choose to the right as positive, whenever acceleration is to the left, acceleration is negative. Deceleration occurs when the acceleration is opposite in the direction of the velocity and our speed decreases. We slow down. So remember, velocity was a vector, speed is just a scalar. So you don't worry about sign there. So if we are going less quickly, we are decelerating. And this is one example of deceleration. Here is a car moving to the left and is going rapidly to the left at minus 15 meters per second. So 15 meters per second, but in the negative direction means minus 15 meters per second. And then a little while later, it's going at 5 meters per second. So the same example we had in the previous slide, but in that case, we've been moving to the right. Now we're moving to the left. And in this case, if you worked it out, we'd have an acceleration of plus 2 meters per second. So we are decelerating, we are slowing down, but the acceleration is to the right, so the acceleration is positive. So here are 4 different scenarios. In the upper 2, a car is moving to the right. In the lower 2, a car is moving to the left. We'll make right be the positive direction, let positive be to the right. So which arrow is velocity? Velocity, let's assume the cars are moving forward, we're not backing up. The velocity arrows always point in the direction in which the car is moving. And if we assume that they're all moving at the same speed, so these arrows of same length represent the same variable, then the arrows that always point in the direction in which the car are moving are these longer ones in front of the bumper. So that arrow is velocity. That leaves the shorter arrow on top of the car to be acceleration. So let's label our velocity acceleration arrows so we are clear there. Here we go. So where is the velocity positive? Velocity is positive when it points to the right in the positive direction. Velocity will be negative when it points to the left. Let's do the same thing for acceleration. Same answer. Acceleration is positive when it points to the right and negative when it points to the left. So we can add that information, think that through a bit. And now finally, let's consider what these different scenarios represent. And actually it says it underneath. Where does the speed increase and decrease and so on. So when do we speed up? we speed up. In this example, we can see when the acceleration and velocity are in the same direction. So if they're both positive, we're speeding up, we're going faster to the right. Or if they're both negative, speed increases. Where they're both negative, we're speeding up to the left. So again, keep the distinction between speed and velocity. The velocity is negative, it has a direction, but speed is just how fast you're going regardless of direction. So our speed is increasing when it's in the same direction as the acceleration. Where does the speed decrease, or where are we decelerating? It's when the acceleration is the opposite direction of the velocity. So that's true here. We're moving to the right, but we're hitting the brakes. So the acceleration is back to the left, so we are slowing down. Or here, we're moving to the left, but we're hitting the brakes, so the acceleration is back to the right, and we slow down. That was this example is the one we had on the slide just before the little blue cars discussion began. Here, where the velocity was to the left and the acceleration was to the right, and we were slowing down. All right, so already a lot to keep track of. Some terminology that can be a bit confusing, the difference between deceleration, which is slowing down, and negative acceleration, which is just the direction of the acceleration vector and doesn't tell you whether you're speeding up or slowing down. Another takeaway from this slide is when acceleration and velocity are in the same direction, we speed up. And when they're in opposite directions, we're slowing down. Similar to velocity, where we can calculate instantaneous velocity, we can also calculate instantaneous acceleration. And instantaneous acceleration is the average acceleration in the limit as the time interval becomes infinitesimally short. So where acceleration is still change in velocity over change in time, but our time interval is becoming really short. So we just get a snapshot of the acceleration, not some average over some long length of time, but take as short a time slice as you can and get a picture of what the acceleration is at that moment. All right, once more, I'd like to come and look at a graphical example. This is from the OpenStax textbook. In each of these three graphs, we have time on the x-axis increasing from left to right. And as we move down, we have a plot of position versus time. Then we have velocity versus time. And then we have acceleration versus time. And these are all relating to the same motion of an object, one-dimensional motion of an object. So if we start out with position versus time, just imagine you had like a little matchbox car and it was moving along a straight line down a track, and at periodic intervals you were taking note of its position at a particular time. So after, say, 5 seconds, you noticed it had gone this far. After 10 seconds, it had gone a little farther. After 15 seconds, we're at this position of 50 meters, and so on. So we're just moving straight down our little track. So the position just keeps the magnitude, the position is increasing with every measurement. But you can see that the rate of increase isn't always the same, and that's related to the velocity. And let's just think about that a little bit. Velocity is our change in position divided by time. Rise over run is a measure of slope, and for this plot, our rise is position, delta x, and our run is our time, delta t. So delta x over delta t is rise over run. And so the slope of this line gives us our velocities. A quick note on slope: if the line is parallel to the x-axis, the slope is 0. As the direction of the line becomes steeper relative to the x-axis, then we are having an increase in slope. So here we have a fairly low slope. We're moving at a fairly low velocity. Here the slope is getting a little bit steeper. Our velocity is increasing, increasing, increasing. From here to here, the slope doesn't change. So our velocity here is constant. And then we see the slope is decreasing. So our velocity is dropping. And that's shown graphically down here. As I said, for these first 1, 2, 3, 4, 5 points, we're getting an increase in slope corresponding to an increase in velocity. And our velocity here is going from 2 meters per second to 4 meters per second to 6 meters per second to 8 meters per second. We're having a steady increase in velocity until we get to this point, and then our slope is uniform. So we are going at constant velocity here, and that's what we see here. We have a nice flat line. We have maxed out at 8 meters per second velocity. Our velocity is constant, and then our velocity starts to decrease. Our slope is dropping, and we see the velocity dropping here as well. All right, following the discussion we had before, if we consider what acceleration is a change in velocity over time. And that is the rise over run for this graph. So rise over run is the slope on this graph. So the slope of this graph is our acceleration. And so if we see that the slope remains constant from our starting point up to 20 seconds, that corresponds to a constant acceleration here of 0.4 meters per second squared until we get to this point. So as we're increasing velocity, we have in this example, it corresponds to a constant acceleration. We know if we're changing velocity, we're accelerating. Here we're changing velocity at a uniform rate, so we have a constant acceleration for the first 20 seconds. And then at this point, we go at a constant speed. So our velocity is fixed. There's no acceleration now because there's no change in velocity. And we see that indeed our acceleration goes to 0 along that for that time interval. And then past 40 or so seconds, we start to slow down. We have a decrease in velocity, and that we jump down to here, and we have a negative velocity of -1 meter per second every second as we go forward from 40 seconds. All right, so that's a nice tour of position versus time, velocity versus time, and acceleration versus time for some object. Personally, I find it easier to think through the velocity versus time. So if we take this example again, you might be thinking we're at a stoplight, we hit the gas, and we hit it nice and uniformly. So we uniformly speeding up, speeding up, speeding up, speeding up, speeding up. We get to a traveling speed, and we go at a constant velocity pegged at, in this case, 8 meters per second until here, and then we hit the brakes and we slow down, and we slow down more rapidly than we sped up. So our deceleration rate should be greater magnitude than our acceleration rate, and we see that. Our acceleration rate was at 0.4, and our deceleration rate had a magnitude of 1. And it's negative, so it's -1. But the absolute value of it is greater here. This is a steeper slope. We had a faster change in speed here. Okay.